So the goal of this is to find the mass of the Milky Way, knowing about how the Sun orbits the galactic center. In other words, the Sun orbits, along with all the other stars, our galaxy, the Milky Way, and by knowing how long it takes for that orbit to take and how far away we are from the middle, we can actually measure the mass of the Milky Way in much the same way as we measure the mass of stars, by looking at binary star systems or planets going around them, or we measure the mass of planets by observing the moons that orbit them. So we'll begin by reading the exercise sheet. The mass of the Milky Way. The Sun orbits our galaxy, the Milky Way, every 220 million years, traveling at a speed of 240 kilometers per second. It is located about 8,300 parsecs from the center of the Milky Way, which is called the solar circle. How many times more massive is the Milky Way than the Sun? Or, more specifically, what is the mass of the Milky Way located within 8,300 parsecs from the Milky Way center? Note, 1 parsec is 60 times 60 times 180 divided by pi astronomical units. Notice that means that that's the same number of astronomical units in a parsec as there are arc seconds in a radian, which equals 206,265 astronomical units. Okay, our first step in solving any of these problems is drawing a picture, so we understand what's going on. So what's happening is you have our galaxy here, something like this, and the Sun orbits the galaxy. So let's draw that in. That is called the solar circle. Now we can label the radius of the solar circle little r, and we can call the amount of time it takes the Sun to all the way go around p, just like we do for planets orbiting stars, or just like we do for moons orbiting planets. Next, we have to imagine what we're going to compare it to. Our goal is to find the mass inside the solar circle of the Milky Way. So we can compare it to anything orbiting anything else. So in this particular case, it's asked us to ask how many times more massive is the Milky Way than the Sun. Therefore, we have to have an analogy between the whole Milky Way and the Sun. Here's the Sun in this picture, but in this picture the Sun's the thing doing the orbiting. What we want to do is we want to think about something that orbits the Sun. So something orbits the Sun. That something that orbits the Sun is the Earth, and the distance it is away from the Sun is 1 astronomical unit, and it takes 1 year for it to go around. Now, we can then fill in our table now that we have an analogy. We have the Sun orbiting the Milky Way, so let's put that here. Sun orbiting Milky Way. Okay? And then right here, we will have something that orbits the Sun. So, orbits Sun. And Earth is our favorite thing that orbits the Sun, because we live here. Now, the next thing to do is to use the physical principle. The physical principle we're using is Kepler's third law. And Kepler's third law, as we remember, and if you don't, you can look it up, is that the mass that's being orbited times the period of the thing doing the orbiting is proportional to the same major axis cubed of that same thing doing the orbiting. In other words, to find the mass of the Milky Way, we use the Sun as our test object. Kind of like to find the mass of the Sun, we use Earth as our test object. And kind of like to find the mass of the Earth, we would use the Moon as our test object. Now that we've got our principle, let's fill in our variables in our table. mass, period, semi-major axis. Now this is the mass of the Milky Way, and this is what we're interested in, right? So let's give it a variable name. And then we know that the mass of the Sun, because that's the thing being orbited, is 1 solar mass. So we can put that in as our unit, and we can say 1 there. Alternatively, if you wanted to, you could have put the solar mass there and left the unit blank and found the ratio. You get the same answer both ways. Now, let's consider how long it takes for the Sun to go around the Milky Way. In the problem statement, it said that it took 220 million years for it to go around. So I'm going to put 220 million here. 220. Now million is 6 zeros. 1, 2, 3, 4, 5, 6. Or you could say 220 times 10 to the 6th, or 2.2 times 10 to the 8th. Now that is in years. And it takes the Earth 1 year to go around, so we can put a 1 here. Now the distance is a little trickier, because we know how far away the Earth is from the Sun in astronomical units. It's 1 AU. We also know how far away the Sun is from the center of the galaxy in parsecs. And we also know parsecs are in an AU. Now, it does not matter whether we use parsecs or astronomical units, as so long as they're the same. We cannot use parsecs here and astronomical units there. So, because astronomical units are smaller, let's just put those here, and we know that the Earth orbits the Sun with a orbital radius of 1 astronomical unit. But then we have to figure out what goes here. So we're given in the problem statement that R is, or what we're calling R, is 8,300 parsecs from the center of the Milky Way. So we're going to have to convert our 8,300 parsecs to AUs. So I started out by writing this trivial statement that it's equal to 8,300 parsecs, which is 8,300 parsecs. Now, if we multiply any number by a fraction with the same thing on the top as the bottom, it doesn't change, just like you do when you add fractions. Well, conceptually, that's what we're doing here when we convert units. We want to say what's conceptually the same thing for both. And we want to get rid of our parsecs, and we want to end up with astronomical units. So we want something in AUs here and parsecs here, but we need to have the same physical quantity on the top as the bottom. And that's where we come by here and we say, oh look, 1 parsec is 206,265 astronomical units. So we'll fill those right in here. Now that we've filled those in, we can cross out our units, and we ended up with just AUs. So on our calculator, we will say 8300, that's 8300 parsecs, times 206,265 astronomical units per parsec, and that equals a very big number here in astronomical units. That would represent the distance the Sun is from the center of the galaxy in astronomical units. Now notice we only gave this to 2 significant figures, so we will probably round this off, which will make sense. Now rather than looking at all these numbers and copying them down, I'm going to put them in scientific notation or engineering notation, my choice, and I will pick, so I can write this down as 1.7 billion, AUs from the center of our galaxy is where the sun is. So, now that we've done that, we can then fill in our table with 1.7 times 10 to the ninth, or 1.7 billion AUs here and 1 AU there. Notice usually we use numbers that are in sort of normal numbers and big units in astronomy, but in this case here we already have pretty big units for the Earth-Sun, but they're teeny tiny compared to the Milky Way, and we're comparing something really big with something relatively small. So we have to have real big numbers, not just numbers that are big because we measure them in something normal like meters or something. So the big picture here is that we have the sun orbiting the solar circle, we have the Earth orbiting the sun, and we're comparing the system of the sun and the Milky Way with the system of the Earth and the sun. And we're going to use Kepler's third law, which says that the mass being orbited times the period of the orbit squared is proportional to the semi-major axis cubed. And now that we know everything for our reference object, which is the Earth orbiting the sun, and we know everything but what we're interested in for the sun orbiting the Milky Way, we can now solve our problem. The trick is we have to set it up like a ratio. So what is proportional to mean? It means equals in ratio. So the first thing I'm going to do is copy this over and then solve for the mass. So we have mp squared is proportional to r cubed, so we'll write that down. And we want the mass all by itself. Now remember, you can treat proportionality symbols kind of like they're equal signs for the purposes of multiplication, division, powers, and roots. So I'm going to divide both sides by the period of the orbit squared. Now notice something. This does not mean any one thing. It means if we compare things to each other. So this principle works for both the Earth orbiting the sun and the sun orbiting the Milky Way. But what we're doing is we're going to compare the two. So now we get the same type of relationship as we've had for many weeks now, since we started covering Kepler. And now what we're going to do is we're going to change this proportionality to an equal sign, and the way you do that is by putting in a ratio. So we're going to put in a ratio for the mass, a ratio for the semi-major axis, and a ratio for the period. Now the first thing I do when I solve ratio problems is I put in parentheses ratios following the same format as my proportionality. So in this case I have the mass proportional to the semi-major axis cubed over the period squared. So I'm going to make sure that this ratio gets cubed and this ratio is squared. So I'm going to put my ratio of my periods there, my ratio of my semi-major axes there, and my ratio of my masses there. Now the next thing I do is I'm going to take and copy over from here down to here. Now this is what I'm looking for, and what this really asks is how many times more massive is the Milky Way than the sun. So that's what I'm going to put over here. The mass of the Milky Way is right here, and then this is going to be one solar mass, or the mass of the sun. And remember, a circle with a dot in the middle is our symbol for the sun. Now what goes here, it has to be the corresponding values from the top to the bottom. So now let's see, this was R, so that's got to be R. So now we've got to look here. So this is 1.7 billion AUs divided by 1 AU. Notice my astronomical units cancel. So what's left over inside that is a unitless ratio. So now I'm going to copy over the period ratio and put it here. So this would be 220 million years divided by 1 year. And now I'm going to calculate these ratios first before I cube and square. Now, when you have an equal sign like this, you're applying that the same thing on the left is equal to that. So this is the subject, that's the verb, and then that's the predicate. So now I can copy over here and put it there. So I'm going to have my ratio of my masses is going to be equal to this number divided by 1 is 1.7 times 10 to the 9th. So 1.7 times 10 to the 9th. And this number in years out of 1 year is going to be 1, 2, 3, 4, 5, 6, 7, 8. 2.2 times 10 to the 8th. Now, before I cube and square, I'm going to ask myself, what am I expecting this to be? Okay, if there wasn't a cube or squared, this number is just about a little less than 10 times that number. So you get something like 10, and that makes no sense for the mass of the Milky Way. We're expecting something a lot bigger than that. But we're going to cube this, which means this number times itself 3 times, divided by this number times itself twice. So if they were the same, then it would just be the same as this number here. Because they're not, it's probably going to be about 100 times more. That's probably my guess. So now, to show that on the calculator, here's the number here, left over on my calculator, so I keep my additional digits, and I'm going to cube it. So I'm going to say, oh, I have an X cube button right there. So I will say Shift cube, and there we go. 5.02 times 10 to the 27th. And similarly, on the denominator, we have 2.2 times 10 to the 8th squared, so I'm going to say 2.2 times 10 to the 8th, and I pushed my EXP key, means times 10 to the 8th, and then hit my squared button, and I get 4.84 times 10 to the 16th. Now, notice something. 5 and 4.8 are about the same. So that ratio will be close to 1. The ratio of 10 to the 27th to 10 to the 16th, well, they're exponents of the same thing, so we can take 27 minus 16, which is 11. So we're going to get something like 10 to the 11th. So on the calculator, that would be 5.02 times 10 to the 27th divided by 4.84 times 10 to the 16th. And that is equal to 1 times 10 to the 11th. 1.0 in our case times 10 to the 11th. So we can see that there are 10 to the 11th masses of the sun in the galaxy, at least inside the solar circle. Now, what does 10 to the 11th mean? If I was going to do this in actual, like numbers with words, I don't know what 10 to the 11th, what that is necessarily. So I'm going to say, you see these E and G keys down here? I'm going to say shift that. Oh, that's backwards. How about that one? Yeah, look at that. It says 100 times 10 to the ninth. Well, I know that 10 to the ninth is a billion because 3 times 3 is 9, and 3 minus 1 is 2. So it's a billion. So I know the answer is now 100 billion. Now, if I go back to the question says how many times more massive is the Milky Way than the Sun? So we need to answer that question. So finally, we answer the question, the Milky Way is 100 billion times more massive than our Sun. So now we have answered the question about the mass of the Milky Way.